Good afternoon, everyone. Today is November 18, 2020, Wednesday. We have a second lecture on transformers. It's a continuation. So we'll have a review initially, and then we'll discuss several important theoretical aspects of modeling transformers. Everything will be considered as an ideal transformer. We review what's an ideal transformer. Then we have some techniques in how to solve circuits, still considering an ideal transformer. And then we have exercise towards the end. The exercise I will let you work, and next session on Friday we will continue and work on those problems. You may ask, why do we have ideal conditions? Ideal conditions are usually necessary when we want to simplify modeling and analysis and simplify how we solve a circuit, either by hand or using a computer. Okay. Ideal components are typically lossless. That means there is no loss, there is no power dissipation, and it's very possible that we just assume that we have 100% of efficiency, which is not true in reality. That's why we call ideal, because they are supposed to ideally convert 100% of the input power into the output power. In real life, we have losses and we have effects that are more complicated than the ideal situation. So sharing my screen, and we will start from where we stopped at the previous lesson. Okay, just a minute. Sharing the screen. I should have here first page is a review. So this is what we discussed so far, just a review so we can catch up where we stopped. You see here two main boxes, okay? And I'm just changing my pointer to a laser pointer. So there is a box here and a box towards the bottom. The box on the top, you see a typical model for a transformer where we use mutual inductance. A mutual inductance happens when you have two windings. The windings could be in air, okay? So the flux lines are close to the air, or they could be in the same core. A transformer is made in the same core. So the windings or the inductors or the coils, they have a very strong coupling. What means strong coupling? Most of the flux lines from the first winding will be captured by the other winding. Just few flux lines are escaping from this, because in a real transformer, even though we have a material, we have some air where some flux lines could close, and that would be what we call leakage. That means some flux lines are leaking from the main path. But this is a magnetic circuits, and I recommend you, if you are interested in that, to have another course where you can understand principles of energy conversion using magnetic circuits. Yeah, here we are trying to understand transformers in a more general perspective. So the top box shows that I have a winding with self-inductance L1, another winding with self-inductance L2. There is a mutual inductance. So what's a mutual inductance? Current that circulates on this loop will induce a voltage on the other side, and the reverse is the same. current circulating on this loop will induce a voltage on the other side. So the total voltage in your KVL analysis would be, see, if you just use a KVL, a mesh here, you start minus V1 R1, and then you have a voltage across inductance, which is L1 dI1 dt. Okay. However, we have an effect that comes from the other side, and in this case, you see there is a plus for the mutual inductance multiplied by the current, the variation of current on the other side. And here it's a plus, and this is a minus. Okay. We discussed this last class. So how can we identify when it's a plus or minus? There's a diagram in the previous lesson where you have several connections, but pretty much you can do like this. Pay attention if the currents enter the dot or enter the non-dot. So look, I1 here is coming this way towards the dot, okay? And I2 here is coming this way towards the dot. So that means they will be adding on their mutual effect, because this is approaching the dot and this is approaching the dot, so I have a plus. Here is the same circuit, but I have a reversal here. Look, dot this side, non-dot here. So that means I2 is approaching where I do not have a dot. So the mutual will be negative. Look, minus and minus, okay? So pretty much that's the way that helps you to identify very easily if the mutual effect will have either a positive or a negative. If both are going towards the dot, it is a plus. If one of them is reverse, either on the left or on the right, then there is a minus. Okay. Great. And sometimes we use this to define our circuit analysis. When you have a circuit with self-inductance and a mutual, one way is to define these equations, but then you have to pay attention if you should have a plus or a minus in the mutual effect. When we define what is an ideal transformer, we have here that the voltage ratio from primary to the secondary, okay? One means primary side, two means secondary side, would be directly proportional of the number of turns on the primary to the secondary. See, 1, 1, 2, 2, okay? However, it's opposite for the current. See, I have N1 and 2, and here I have I2 and I1. So this little box here is very important for you, because if you have a problem that says you have an ideal transformer, the first thing you do is take your pencil or your pen and write on the side that V1 divided by V2, that fraction, is equal to N1 divided by N2, which is equal to I2 divided by I1. From there, you have all the relationships for an ideal transformer. In addition, because your transformer is ideal, you don't have any internal resistance in your windings. We know that in reality, a transformer has a copper wire that you have to wind. So that copper wire will have a resistance, but we are neglecting that. And also because you have a core, that core has properties that will define if you have losses, okay? Then we have to discuss this with magnetic circuits. So we are assuming that there are no losses on the magnetic core, no losses on the copper windings, and there is no leakage. You know, all the flux in one winding is captured by the other one. So this is an ideal transformer. In that case, the input power, which is voltage on the primary multiplied by the current on the primary, should be equal to voltage on the secondary multiplied by the current on the secondary. Another thing you have to pay attention is A transformer only works if you have variation in your voltage or in your current. Okay? So when you have a DC circuit, a DC voltage, if you do not have a switch that you turn on and turn off, if you just take a DC voltage and apply to a transformer, what happens in reality, in real life, is you're going to have a transient, but when the transient vanishes, you are going to have an exponential solution. You have a DC current flowing, and because the DC current flowing through the winding will give you a voltage equals 0, because V is L di dt. There is no voltage variation. Because there is no voltage variation, there is no flux variation. If there is no flux variation, there is nothing captured on the other by the other coil. So transformers are not made for DC circuits. Transformers are made for AC circuits. Typically in this course, we assume sinusoidal voltage variation, because that's the easier way to solve. So the way to solve transformers with sinusoidal voltage source is applying phasor analysis. That means you need complex numbers. And in addition, you also need KVL and KCL, mesh analysis, and node analysis. So everything you have been learning so far in this class comes together now that everything you had in the previous tests and exams and homeworks, they are necessary as, how to say, unified knowledge to evaluate transformers. So this is just a review, okay? Now let's go to the next slide. Next slide is an example. And when I finished my class last time, I gave you two problems. They were examples. I asked you to take a look. Here we have the solution already. So let's see. We have a transformer. The transformer is a model here with self-inductance and a mutual. So we have to use KVL on the mesh on the primary, KVL on the mesh on the secondary, and we have to see if the mutual will be adding or subtracting. Okay, I have plus plus, look, plus plus. Okay, great, but see, I1 goes this way, isn't it? So I1 is the mesh current. So I1 is entering the dot. If the mesh current goes this way, the mesh current leaves the dot. See, remember that? When one current goes to the dot and another current goes to the non-dot, look, comes here, okay? I have a minus on the mutual inductance. That's why I have this minus here. Look at the equation here. There's a minus here, okay? So what we do, we go back to the circuit. We see that there is a voltage source, 10 cosine of 2 pi 10 into 3t. That means omega is 2 pi 10 into 3 radians per second. That's the omega. So I will redraw the circuit, and I will substitute using impedance and reactance. So C1 is minus J divided by omega C1. L1 is J omega L1. L2 becomes J omega L2. C2 becomes minus J divided by omega C2. So from the time domain, I redraw it using the phasor domain. And then I write my equations. So I can write an equation here on this side, KVL here, KVL here. I have two equations, two unknowns. And then when I use that formulation, I can find eventually IL, because that's the question here. What's the current flowing through the resistance? So IL is given by this equation in the frequency domain or phasor domain, okay? So after you solve it, what you have here, J omega M multiplied by the phasor voltage Vs divide by this denominator here, which is a complex number. You can do that by hand. You can do that in your calculator or using MATLAB. At the end, IL will be a phasor that is 139.5 phase 142.2 degrees. Okay, why it's written like this? Because that's the mathematical notation. Okay, this is the Euler's formulation, but pretty much we know that this is the polar form where this is the magnitude, what's in the front of E. Then I have a J, and what's multiplying the J is the phase shift. So from here would be the same as 139.5. Then we use that, how to say, that bracket that looks like an L, and then the phase inside. It's the same thing, but this is the way that mathematicians and physics people use. Okay. So from here I can have the time domain. The time domain we just write in the cosine form because cosine is the reference. So I have 139.5 cosine of the same angular speed that we have here. Okay, and then I take the phase shift and I put there. So from the polar form, we easily write the time domain in cosine. If you solve this in a calculator and you have your IL in the rectangular form, that means you have a real plus imaginary multiplied by J, you have to convert to the polar form because the only way to express your time domain equation is from the polar form. Okay, let's go to the next problem. This is solved there, so you just have to read and understand. So here we have another example. I want you to find all the currents and the voltage, and I want you to assume that your voltage VG is 2500 cosine of 400t. So 400 is the angular speed. That angular speed will be useful for your impedance. However, your transformer is considered to be ideal. When you work with a problem that the transformer is ideal, you do not use the formulation of self-inductance and mutual inductance. You have to use the formulation that V1 divided by V2 is equal to N1 divided by N2, which is equal to I2 divided by I1. So the first thing you do is write that, okay? And then use that formulation. See, I start from my transformer and I make a substitution here for the reactance. And then I assume that I have a voltage V1 here, V2 here, and then I write the expressions for ideal transformer. Okay, let's go there. VG is phasor voltage, such as magnitude is 2500, phase 0, because it's cosine of 400t. Omega is 400. J omega L here is 2J. See? And I write it. And for the other one is 0.05J. So I calculate here and I write here. I calculate here and I write here. The resistances are the same. I assume that I have a primary voltage V1 and a secondary voltage V2. Okay. So I write equations for mesh 1, mesh 2, plus the transformer equations. For mesh number 1, you start from here, this terminal. I have minus VG plus voltage drop here and here, which is I1 multiplied by resistance plus reactance. It's here. Then I have plus V1 equals 0. Okay, mesh number 1 is done. That's the equation. For mesh number 2, I start from here, minus V2. Then I have a voltage drop, which is I2 multiplied by that. Look, I2 multiplied by the total impedance. Then I return and I close the mesh, it's equal to 0. So I have equations for mesh 1 and mesh 2. However, I have to also consider the transformer relationships. So these are the transformer relationships. V1 divided by V2 is equal to N1 divided by N2, which is 10. Okay, here we have, see, 10 to 1. Okay. and I1 divided by 2 is, and 2 divided by 1 is 1 divided by 10. So V2 comes here. So V2 is V1 divided by 10. It's here. And I2 comes here. I2 is 10 multiplied by I1. So I take these relationships and I substitute in the mesh equations. That's what I have. And I make everything in terms of I1 and V1. So I have two equations and two unknowns. The unknowns are phasor current I1, phasor voltage V1. That means current to the primary side, voltage on the primary side. So I can write an equation here. The equation, I take VG and bring to the right hand side. Okay, so I have this coefficient multiplied by I1. This is 1 multiplied by V1 equals to VG on the right hand side. It's here. Here it's 0. I keep 0, and I have V1 has a minus 0.1. It's here. And I1 is 10 multiplied by whatever is in the parentheses. I have 2.375 from here and 0.5 from the other coefficient. So I have here a matrix with complex coefficients multiplied by I1 V1 equals to that vector. I have to invert that matrix. Okay, so how do I invert that matrix? Well, you can invert by hand. I gave you an equation several weeks ago that you can invert by hand. Or you can type this inside MATLAB or Mathematic or even a calculator and invert that matrix and multiply by that vector. And from here, you find I1 and V1. When you find I1 and V1, you can define I2 and V2 because you have the transformer relationships. And then from those phasors, you can write the time domain formulation in cosines. So this was a solution for two problems. I would like to change the discussion now towards what is impedance at the input. Usually we define impedance at the input, and the input could be whatever is connected on the primary. But sometimes you also want the impedance at the output. The discussion is the same. How can we define impedance? Okay, so step back. How do you define resistance? Resistance is DC voltage divided by DC current. Okay, so the same thing could be done in AC circuits. Impedance is defined by phasor voltage, that means a complex number, divided by phasor current, another complex number. So the impedance is a complex number. That means it can be written as real plus imaginary part. When you write an impedance real plus imaginary part, if your imaginary part is positive, that means your impedance has a resistance, which is the real part, plus an inductance. That's why I have plus J. If your imaginary part is negative, that means real part minus J something. That means that impedance is a resistance plus a capacitor, because a capacitor will give you a negative value on the imaginary part. Okay, that's the definition of impedance. So if you look to this circuit here, this is again the mutual. Okay, so I have a self-inductance here. It's already giving J's, so I don't have the parameter values. I already have the complex values. So this is the self-inductance, and this is the mutual inductance. Okay, so I want to find Z in. So what's the Z in? If you look to the terminals A and B, what's the impedance given by this circuit to that particular voltage source? So if I find I1, I take that voltage and I divide by I1 and I find Z in, okay? So how can I find Z in? Well, from this circuit, we know that Z in will be given by the equivalent value here, okay? And the I1 could be defined by that voltage divided by Z. In your book, I skipped that, but in our book, if you read, you can see that when the mutual inductance is either positive or negative, your impedance doesn't change. The voltage relationships, they change, but the impedance doesn't, okay? I didn't include this here because I just want to illustrate. There are another way to do the same impedance analysis. But this slide here is very important because it helps you to define impedance for ideal conditions. Look, we know that for an ideal transformer, V1 is for V2 the same as N1 is for N2. So there is a direct relationship, which is the inverse of I2 is to I1, okay? So how do I define impedance on the transformer, not on this circuit? I could take the primary voltage V1 and divide by I1. So that would be impedance on the primary side. How is the impedance on the secondary side? I take the secondary voltage V2 and divide by secondary current I2. So that's Z2. Great. Now come here. So take these two boxes and let us help to understand what happens in an ideal case. Let's start from here. Let's take N1 divided by N2, which is the turns ratio. And I want to square it. Why I want to square it? Because it's going to help me to get to my formulation. So I start from N1 divided by N2 and I square. When I square, I will have the same multiplied twice. But then I replace the first N1 divided by N2 by V1 divided by V2. And the second one, because it's a square, I replace by I2 divided by I1. Okay, so pretty much what I'm doing is when I square, I take the voltage ratio and multiply by the current ratio here. Then I bring kind of quickly I1 to the side. So I have V1, I1. Look, I bring here. And V2 goes on the other side. So V1 divided by I1 is Z1. Look, Z1. And I2 divided by V2 is the inverse of Z2. Look, inverse of Z2. So what I have, if I start from here and I skip here, I have N1 divided by N2 square is equal to Z1 divided by Z2. Great. So this is another relationship that will help me when I have ideal transformers. The impedance on the primary has a relationship to the impedance on the secondary directly proportional of the turns ratio square, okay? So we use this formulation together with this because they are all related to an ideal transformer, okay? For example, here I have ZL, okay? And I want to find what is Z in, and I have the turns ratio, and my transformer is ideal. I'm gonna use exactly this equation here, okay? Because in this case, I will take 1 divided by A square, and I will take the load impedance and reflect on the primary side, okay? So a transformer will help you to increase or decrease the impedance depending on the turns ratio, okay? For a real transformer, you still have to consider losses. But for an ideal transformer that has 100% of efficiency and no losses, you just use the formulation of N1 divided by N2 square is equal to Z1 divided by Z2. So you can take the load on the secondary and reflect on the primary, or you can take your primary and reflect on the secondary. So this reflection, that what we say, is primary side reflect to the secondary, or the secondary side reflect to the primary, is a way to make the calculations of impedance transformation a little easier. So transformers are usually used for matching impedance because the turns ratio will help you to that. In long past, we used to have headphones that they were high impedance because they were made from crystals, ceramic crystals. They were typically 600 ohms, which is supposed to be a high impedance. So if you want to match 600 ohms with an amplifier that has an impedance of 8, then you need a small transformer to match. Okay, so transformers are used for matching impedance of amplifiers, audio amplifiers, radio frequency amplifiers, high frequency transmitters, antennas, receivers. That's another reason we use transformers. So we can use transformers for energy conversion. That's what typically we use for power distribution, or for analog circuits, low frequency or high frequency, we use for impedance matching. Now, let's keep a little bit this discussion of impedance on the side, and I want to show you two types of equivalent models. In this course, we don't have time to go through these equivalent models, but it's important for you to at least understand. I could start from a transformer that has self-inductance and a mutual, and I would like to replace, see, what I want is, on these terminals, I want to replace this whole thing by this equivalent circuit. Okay, we call that T, is a T equivalent model. See, T, because it looks like a T. Sometimes you say Y, because you can imagine that it's like a Y. Okay, where the Y here is kind of a little bit level and straight enough, but it's either T or Y equivalent model. How can I do it? Well, you can look in your book. This is discuss that, but I will show you quickly. I go to the next slide. I will write the equations, okay, for this, and then I write the equations for that circuit, and I see what is the equivalence on the matrix equations, okay? Then you see that for those to be equivalent, I will take the self-inductance and subtract the mutual to be this parameter. I take this self-inductance and subtract the mutual to be that parameter. And here I have the mutual, okay? So this is typically the transformer model that we use a lot. If you go to a lab and you want to take a transformer and define the equivalent circuit, we usually assume to be a T equivalent model, but we also use losses in that case. Here we are not having any losses, don't have any resistor. So you see that from here to here, I have what? The Lx, which is the self-inductance minus the mutual. So this is a small inductance compared to the self-inductance because we are subtracting, okay? And then I have the mutual. So in this circuit, what's the beauty of that circuit? There is no coupling. So when you use a T equivalent model, you assume this inductance to be the leakage one, this the magnetizing one, this the leakage. And when you write the equations, You just write KVL, KCL directly. There is no need to even think about the mutual effect anymore. So that's the great thing of a T equivalent model. Okay. So a T equivalent model allows a very convenient matrix formulation. Look, if I use my T equivalent model, I have V1 and V2 is equal to this matrix multiplied by I1 and I2. Okay, so this is extrapolation of your mesh analysis. Now, instead of a T equivalent model, we can use something called a pi equivalent model. So why it's a pi? Because if you look here, see, there is a branch here, there's a branch here, looks like the letter pi. We also call it delta. Why? Because delta, because looks like a triangle here, okay? So you can say it's a pi equivalent model or a delta equivalent model. We can write equations. I can write mesh, 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 but then I have to work with algebra, okay? See, I have to work with this algebra. It's possible. I have done that in the past. Not a big deal, but it's possible. But the simple thing to do is I already had a T model, which is Y. Then I have a pi, which is a delta. So if I go back to my initial classes, initial lessons, and take the transformation from Y to delta, that's what we do. We take a T equivalent model, which is a Y, and I make a transformation to a delta. So I apply that, I have those relationships, and then I have the parameters here. So you see that the parameters are a little more complicated, but you can see that this parameter depends on the self-inductance and the mutual. This parameter here depends on the self-inductance and the mutual. This is the same. So you can have also a pi or a delta equivalent model. Okay. Here we have a discussion again on the input impedance. And this, by the way, is in our book. I ask you to please do read and review the lesson today in our book. And when you write what's your reflected impedance, eventually you find that your impedance is this value here, which is the input. We have been discussing the same problem as before, okay? Another thing is to use the same discussion of impedance, but using a T equivalent model. Look, the parameters here are the mutual comes here on this branch, and the inductance here are the self minus the mutual. See, 5 minus 2 is 3, and 20 minus 2 is 18, okay? When you have this, you no longer use the circuit here, and you just go to the equivalent model, and there is no mutual here. So you write a KVL directly here, KVL directly here. You have a matrix, and you have, of course, the same impedance as we calculated before, okay? And also we can replace a transformer by the equivalent Thevenin. So there's a discussion here. It's also in our book. You have to read example 8.51. But what I do is across terminals A and B, I replace this circuit with this circuit, and then I have an equivalent Thevenin. Or I can, instead of looking to terminals A and B, I can look to the terminals C and D, and whatever is on the left, I replace by this equivalent Thevenin model. So one would be a model considering the terminals A and B. Another would be a model consider the terminals C and D. Okay, so that should be a way to have a transformer replaced by a Thevenin equivalent. In the power grid, we can discuss this a little bit next time. We use for power conversion. I'm going to discuss this next class. And I also discuss next class about three-phase transformers. But what I want you to do from today until Friday, our next class, we have three problems. Problem number 1 is here. Problem number 2 is here. Problem number 3 is here. 3 problems. So between now and Friday, please do review this lecture. read your textbook and try to work on those 3 problems. Next lesson will be a discussion of those problems and also um, kind of completing the introduction on transformers for electrical power conversion. And after, we'll be prepared for our next step. Okay, next step, no, next test. I stop sharing, and if you have any questions, wait. Yeah, I stopped sharing already. So do you have questions? It's 2:44. I can end the class now. You are welcome to leave. You are welcome to stay and ask me questions. I have another class in a few minutes, so I can entertain a few questions. Otherwise, have a good Wednesday. Be well, be safe. Okay, thank you. See you on Friday. We still have a few students in the session. If you have questions, you are welcome to ask. Otherwise, I'm going to end. Okay, thank you. Bye.